How are you, my friends? This is basic math terms. I'm continuing with the Calculus 1 terms. The Calculus 1 terms started with part 30. And just a little note here, the algebra terms, you can find them in parts 1 to 18. Pre-calculus terms, you can find them in the videos parts 19 to 27. And the statistics terms were parts 28 and 29. So this is part 36 of the basic math terms, higher derivatives. There are 8 words we would like to see. First, derivative test, higher order derivatives. Second, derivative test, infinite limits, which is vertical asymptotes, limits at infinity, horizontal asymptotes, curve sketching, indeterminate forms, 0 over 0 or infinity over infinity, L'Hopital's rule. Now, the first derivative test, we do it to test where the function has a local minimum or local maximum. This is from lecture 17. So we check f prime. If f prime is negative to the left of the number c, and f prime is positive to the right of the number c. So there is a local minimum. So this is what we call the first derivative test for local extrema. Also, if we have the derivative greater than 0 positive to the left of c and f prime is negative to the right of c, then there is a local maximum. If there is no change in the sign of f prime, then the function has neither a max nor a min. This is one quick example from lecture 17 also. Function f of x, 2x cubed minus 3x squared minus 36x plus 7. If we find the derivative and we factor the derivative, it will be 6x plus 2x minus 3. So this is an application on the first derivative test. We do table of signs. Table of signs you can see in the complete algebra course, lecture number 25, how we do these tables. So we can put the factors here, x plus 2, x minus 3, and here we put f prime because this is the first derivative. We check a point here from minus infinity to minus 2, another point from minus 2 to 3, another point from 3 to infinity. Then we see f prime is increasing, positive, then decreasing because it's negative, then increasing, positive. So we conclude that the function f has a local maximum at minus 2 and local minimum at 3. How to find the max and min? We take minus 2 and we replace it in the function here. We get f of minus 2. That's the max. Local minimum, take x equal 3. Replace it in the function here. We get the minimum will be f of 3. Higher order derivatives. We can find higher order like nth derivative of the function. So we can write it here like this. Nth derivative of x will be the nth derivative of x. We can write it in this one, capital D, x, f of x. We can write it in 3 ways, either operator notation or differential notation or function notation. So we can write here y prime of x, dy over dx. That's the first derivative. Dx of f of x. So the first derivative of f. Dy over dx, also the first derivative of the y, and y prime of x, and the same for the other, second derivative, third derivative, until we reach the nth derivative. So this is an example on higher derivatives. Nice function we have, f of x is equal x squared times ln of 3x. Let's find the 5th derivative of this function. As you can see in the answer, it will be, the 5th derivative will be 4 over x cubed. Let's do it in details. First, we try to find the first derivative f prime. Now we can see here a product x squared times ln of 3x. So we can remember directly product rule, u prime v plus v prime u from lecture number 7 in the calculus 1. So f prime will be the derivative of x squared times ln of 3x plus the derivative of ln of 3x times x squared. Now the derivative will be 2x times ln of 3x. This one here, ln of u, will be u prime divided by u, if you remember, times x squared. So it will be 3 over 3x. Let's simplify all that. So we get 2x ln of 3x plus only the x. This is the first derivative. To find the second derivative, we can apply for the first term here the product rule again. 2x all prime times ln of 3x plus the derivative of ln of 3x times 2x plus 1, which is the derivative of the x. So we can proceed here. 2 times ln of 3x plus 3 over 3x times 2x plus 1. Simplify more. It will be the second derivative, 2 ln of 3x plus 3. Now let's find the third derivative. There is no product rule here in the third derivative. It will be 2 constant times 3 over 3x plus 0, which is the derivative of the 3. So this third derivative becomes 2 over x. Let's find the fourth derivative. So it will be 2, this is a constant. The derivative 1 over x will be minus 1 over x squared, as you remember. So it will be minus 2 over x squared. Now let's find the fifth derivative. So I take minus 2, this is a constant here. Then I have 1 over x squared. So the derivative will be minus the derivative of the denominator, minus 2x, over the denominator squared, which becomes x power 4. Minus 2 times minus 2 becomes 4x. You can cancel here 1x. You get 4 over x cubed. And this is the fifth derivative of the function f. Now, the second derivative test, also for local maxima and minima, but we use the second derivative. If f double prime greater than 0, then f of c is the minimum value of the function on that interval I. So if f double prime, the second derivative is positive, so we call this concaving up. So there is a minimum here. See, the graph is concaving up. If f double prime is negative, the function here is concaving down. Let's look here at the concavity and the inflection points. So we can say that the function f is concaving upward in some open interval if the graph of the function lies above the line tangent, which is line L here, tangent at the point A. So if the graph lies above, so this is concaving up. So there is a local minimum. Same idea. The function is concaving downward if the whole graph lies below the tangent line, and f double prime is negative, there is a local maximum. And if there is a change in concavity, then we have inflection point. So the inflection point occurs where the second derivative changes the sign, the concavity changes. Maximum or minimum where the first derivative changes sign. We can have a nice example. We have seen it in lecture number 19. So we have an inflection point here. This is concaving down, this is concaving up. Also at the corner here, we can have an inflection point. You can check that, please. Infinite limits, this is lecture number 4, and the vertical asymptote. If we have a limit of the function as x goes to a is equal to plus infinity or minus infinity, so the function is increasing without bound, then we can say that the line x equals a is a vertical asymptote. So this is infinite limit, and we have a vertical asymptote at x equals a. Limits at infinity, this is related to horizontal asymptotes. We have the limit of the function as x goes to plus infinity, and the limit is L, it's a number. Or we have the limit of the function as x goes to minus infinity. Also, it can be L, another number. So if we go here without bound on the x, and the limit is a number, then this is a horizontal asymptote. The horizontal asymptote, always we can write it as y equals L, horizontal asymptote. Curve sketching, this is lecture number 20. There is a nice idea. This is a rational function. You can check lecture number 20 for more questions on curve sketching. Also, there are many videos, all the exams questions for graphing, maybe parts 1, 2, and 3. One simple important question you have to check at the end: does the graph cut the horizontal asymptote? When you find the horizontal asymptote, you have to check if the graph will cut it or not. So what do? You put the function itself, this is the function, 3x over x squared plus 1 equals the horizontal asymptote. Now, in this case, the horizontal asymptote y equals 0. So you put 0 equals this function, cross multiply, 3x is equal to 0, x will be 0. So there is a value for x. If x is 0, replace it in the function, you get 0 over 0 plus 1, which is 0. So yes, the graph here will cut the horizontal asymptote at the point 0, 0, which is the origin, or it can be any other point. L'Hopital's rule, this is lecture number 21. When do we use this rule? When we have indeterminate form of 0 over 0 or infinity over infinity. So if you are finding the limit of the function f of x divided by g of x as x goes to a, and it happened that we find 0 over 0 or infinity over infinity, then we can use L'Hopital's rule, which is the limit as x goes to a of f prime, only f prime on the numerator, divided by g prime of x. So this is not the quotient rule, remember. This is L'Hopital's rule, and the limit on the right should exist. Sometimes you can use L'Hopital's rule 2 times or 3 times normal. I have mentioned this one also. Indeterminate form, it can be plus infinity over plus infinity or minus infinity over minus infinity, involving infinities. Thank you for watching. If you like the video, you can subscribe and share it with your friends. I hope I can see you in another video with another topic. Thank you guys for listening.